Welcome to SciPy, everybody. My name is Mansi Shah, and I'm here with my colleague Kevin Lacaille, and we're really excited to present for y'all a tutorial on analyzing coastal erosion using geospatial imagery in Python. I guess we should start by introducing ourselves.
Hey, I'm Kevin Lacaille. I'm a software engineer at Planet, and I've been there for about a year. And both Mons and I are on the developer relations team, where we build tools for users like yourself to help ease the pain when using any sort of geospatial data or our data in particular.
My name is Mansi Shah. As Kevin said, developer relations team at Planet Labs. Also been there for a little less than a year. My background is it's kind of varied. It's like environmental science, data science. I sort of come at it from all different angles. So don't feel worried if this is your first time doing anything geospatial related with Python. We are here to help. All right, so what are we going to do today? We are going to be talking about first the core geospatial concepts associated with remote sensing analyses and computer vision. And then once we cover those, we're going to look at them in Python. So how can we use Python tools to perform some of these analyses and like do this raster processing? And then finally, y'all are going to apply all of what you've learned to a real world scenario of coastal erosion. Any questions so far? Okay, cool. All right, so just starting with some core geospatial concepts, just out of curiosity, who's worked with geospatial data before? Okay, so a handful, cool. Anyone completely new to Python? It's okay if you are, yeah? Okay, awesome. You're very brave to be here, so awesome. All right, so first thing to know about geospatial data, spatial data is special. There are characteristics of working with spatial data that are different from working with other kinds of data or even other kinds of imagery. For example, geospatial raster imagery can be multispectral, so that means that the imagery has multiple bands. For example, a visual color image you're looking at might be made up of the red band, blue band, and green band that are all combined to get you that visual image. And that's a consideration to keep in mind. Geospatial data is also spatially referenced, which means that an image you're looking at of the Earth ties to a specific place on the Earth itself. So it's not just an image, but the image ties to like a physical location. And it also, because of this, has spatially relevant metadata that helps tell you where on the Earth you're looking at. Just an example of how raster data works. So if you look at the image on the right, just say this is like a beach, for example. So you have the jungle or trees, and you have some sand, and then you have water. These are pixels arranged in a grid, and the similar pixels that have similar values, pixels that are similar will have similar values. So if you look at the image on the left, you see that generally all the water pixels would have the same value, all the sand pixels would have the same value, and same with all the tree pixels. The pixels are also represented as numpy arrays. So this is the sort of special feature of it that will allow us to manipulate this data as we go. You might also have heard of the concept of resolution when it comes to geospatial imagery. It's a little confusing because there are so many different types of resolution. So let's just go over them really quickly. The first is spatial resolution. This is probably what you think of most commonly when you do think of the word resolution. So if we're looking at, let's go back to that beach image. Say we're looking at a picture of a beach. Spatial resolution is how much area on the ground does one pixel cover. So for example, if you're looking at that image we were just looking at, you might say, okay, 1 pixel on this image covers a 3 by 3 meter area on the ground. And so your spatial resolution would be a 3-meter spatial resolution. You also have temporal resolution, which is the frequency between image captures. So say you went to the beach in 2018 before COVID, and then you went in 2020 right before COVID hit, and then now you go to the beach again this year. Your temporal resolution would be every 2 years or so, and that's how often you would capture those images. There's also spectral resolution, which gets to that band concept I mentioned earlier. So this is the number of spectral bands we're measuring. Most common, you have RGB and like near infrared, but there might be other bands you're looking at too. And then there's also radiometric resolution. This is bit depth of pixel values. So how much information does 1 pixel contain? This is a little confusing, but I like to think of it in the context of color. So if you have high radiometric resolution or high color depth or bit depth, you'll see colors a lot more clearly. And actually, I have an example of this. So this is a really good example. With low bit depth, if you're looking at this leaf image, it's kind of black and white looking. You might get some green with a little more, but then if you increase your bit depth, radiometric resolution, you get these colors really clearly here. So that's just an example of that. All right, and then talking about the bands again, we are going to be working with multispectral imagery, so imagery that has more than just 1 band of data. So again, if you look at the image on the right, you see a sort of natural color image, like what you might expect to see if you're just looking at the image with your eyes, but that is made up of several different bands, red, green, blue, and others as well. Yes. Oh, no. Yes, please go for it. Yeah. Yeah, that's a good question. I think that's... Yeah. I think that does make sense. Yeah, computationally for sure, but also from a modeling perspective. Yeah.
Definitely, okay. So bit depth goes as 2 to the nth power. So if you have a bit depth of 1, you'll have 2 colors. If you have a bit depth of, well, I don't have the thing here, but let's say 16, which is like our analytic data, you'll have a bit depth of 2 to the 16. So like 10,000 different shades of a certain color. Then you add, let's say, just 3 bands, and you have 3 times all that. So yeah, it scales exponentially. So if you're trying to model something at a very high temporal resolution with years of data, you're going to probably want to lower that bit depth if you don't have like a supercomputer.
Any more questions? So we've talked about some general basic geospatial concepts. Let's talk a bit about the imagery we're going to be using today, which comes from Planet. So Planet has a couple main different types of satellites. On the left is the PlanetScope Dove satellite, which is the same one you see right here. Definitely take a look at it later if you haven't already. It's pretty cool. These ones are about 5 or so kilograms each. They're quite small. They fly in a large constellation and they map the Earth's landmass every day at about 4-ish meter resolution. They're small, but they travel fast, around like 20,000 kilometers per hour. And they take pictures in 8 different spectral bands. We're going to be working with 4 of the bands today, but they take 8. And we also have, yes. There are many different doves that fly around the Earth together, and together they image the whole Earth. I have a picture I'll show you. It'll make a little more sense in a bit. We also have SkySats, which are bigger than these doves, about 100 kilograms. They take higher resolution data, and then they're bigger as well. They're about the size of like a mini fridge, and those are tasked satellites. Did you want to add anything, Kevin, about our sats? We tend to nerd out a lot about this. So, all right. So this was a video. It's not going to work here, but you can see there's sort of a narrow band on the Earth where these doves are circling. So if you imagine the Earth is turning and then these doves are circling the Earth, slowly they'll cover the whole landmass of the Earth as the Earth turns. And here's just another graphic sort of saying the same thing. It's a little bit blurry. All right, any questions? Yeah. Every day, yep. Yeah. High cadence satellite imagery. Cool. All right, let's talk about geospatial tools and libraries. So the good news is Python's open source. We also have lots of geospatial tools that are open source that we use. Some foundational software that's really important. GDAL is a library for reading and writing raster and vector data. And then Proj is used to convert coordinate reference systems, which we'll talk about in a bit. Anyone used GDAL or Proj before? Nice. And then also Python libraries. We've got rasterio, used to read and write geospatial data represented as arrays. Then we also have numpy, which works well because it also works with arrays. Matplotlib is used to plot data, generate charts, and then openCV is a computer vision library used for image processing. Anyone worked with these before? Yeah, nice. Awesome. Okay, the fun part. So, if you all haven't already, go ahead and go to the link on the screen here. This will take you to our repo that we'll use for the rest of the tutorial. You should be looking at something that looks like this. Is everyone there? Anyone want me to put up that link again? Yeah? Okay. All right, so what we're going to be doing now is, before we dive into the coastal erosion example, we're going to be going through some key steps and like working with the libraries for examples before we dive into the main sort of part of the tutorial. So if you go to the repo, it looks like this. As Kevin mentioned, just really quick for the data download piece, there are two ways to use the data that we're going to be working with today. The first way I recommend highly is using Google Colab. Anyone use Jupyter notebooks before? Okay, mostly familiar with that? All right, cool. Yeah, Google Colab is a way to basically run that in the cloud. So you don't have to download the data to your machine. It's all just sort of there, and I'll walk you through that in a second. The second way is to run it on your local Jupyter instance. So then in that case, you would have to download the data and clone the repo. Is anyone here, just so I know, doing this method, doing the Jupyter method? Okay, a few of you. All right. If you run into issues when you do this, you can always switch to the Google Colab method. I'm going to be running through it on Collab here, but just know that if you run into issues, this one is always available. Yes. Yeah, so when we go through these in Colab, the notebooks will, once you work with them, if you add any code or if you change anything, once you exit out, it'll go away. If you want to save it, any changes you make to it, I'll show you in a second. So you'll want to go to, it's kind of like Google Docs where you like save a copy to your personal drive. So you'll want to go to like File, save a copy, and then you can save a copy here and then work with it. And then anything you do will be saved. Yeah. Another quick note, make sure if you haven't already, so for this, you won't need to download data, but for Kevin's part later, you will need the data, and that is a large data set. It took me like an hour and a half to download. So if you haven't already, click on this 0_download_data notebook in the repo, and yes, because data needs to be downloaded. Oh yeah, right here. Okay. But it does take a while to run. So either have it downloaded to your local machine or just run it here through Collab. Yes. Yeah, you can either run it here in Colab if you're using it this way, or you can download it to your local machine. Yeah. Does that make sense? Oh, yeah, true. I need to download it too. When you try to run things in Colab, you might get this message, notebook not authorized or not authored by Google. That's okay. You can just run it anyways. All right, so going back to the repo. I'll just do it later. I'll download it later. Okay, you want to make sure you keep this open in a tab because we'll keep coming back to this. So for now, if you want to click on this first notebook in the repo, 1_rasterio_first look. And then you should be looking at something like this. And then in your notebook, you want to click this blue button that says open in Colab, and then you'll see this page that I'm looking at. Has everyone been able to get to this point? Either open in Collab or on your local Jupyter instance? Okay, great, awesome. So let's talk about reading data with rasterio. So in these examples, later we're gonna be using a different example with Kevin, but in these examples, we're gonna be using an image of Houston flooded during Hurricane Harvey in 2017. So this is real data this imagery was released in the days following Hurricane Harvey. And first responders use this data on the ground to help facilitate rescuing people and just in general rescue efforts during that hurricane. So this is real data that we're using. So first thing you want to do if you're using Colab, you're going to want to run this line. Just by the way, for those of you who haven't used notebooks before, notebooks allow you to run code sort of line by line so you can see what happens step by step. So to run lines in Colab, you want to click this play button that's next to the code cell. And the way that you will know if it's finished is you will get a check mark. No. Oh, okay, great. Ooh, crisis averted. Okay, so run this. Anyways. All right, it might take a second, but after it's done, you should get a check mark. And this, let rasterio install and also data download, you'll have to do it for every notebook that we do today. So just FYI. Has everyone been able to run this line? Yeah, okay, great. All right, so loading a data set. First, we want to import rasterio. So we're importing the package. Go ahead and run this line. And then the data that we just got above, this is us loading the data in. So this third code block, we're opening this data using rasterio and then calling this image in rasterio, calling it SatDat, satellite data. And we're printing this. So here we can see this output shows our data set that we've just read in. Then we can also look at some basic information about our data set. So if we run this next line, we see again the name of the data set, all of these sort of numbers, and then visual.tif. And then we also see the number of bands in this data set. So satdat.count is 3. So we have 3 bands in our data set. We can also work with the bands. So if we run this first line, we can see the indices of our bands. This is important because if you worked in Python before, you know that Python is 0 indexing, meaning if you have a list of values, the first value is actually value 0. It's a little confusing. But with bands, the first one is 1. So first band is 1, then 2, then 3. And then because we know we're looking at a PlanetScope 3-band image, we know the band's order. So you might be used to seeing, if you've worked with geospatial imagery before, RGB, red, green, blue. In this case, our band order is blue, green, red. So by running this line, we're taking our image and we're saying we want to establish the band order as blue, green, and then red. We can also look at the data type and we see it's a unsigned 8-bit integer, and so we know it's stored as an numpy array. Yes. Yeah, I think you'd have to know, you might be able to tell, like if you visualized your image, it might look funky if it was blue, green, red, and you thought it was RGB. If you visualized it, like the colors and stuff would be off, so you would know to flip the bands. That's usually how I find out. I like visualize it and I'm like, oh, that doesn't look right, and then change it. And then we can finally also look at the shape of our image. So if we run this line, we can see that our image is about 4,000-ish pixels by 8,300 pixels. So we get the image of it. Any questions on this first look of rasterio? Sorry? Yeah. Yes. Yeah. What the arrays? They probably have values, but they might also have zeros. They might have some like NaN values as well. Yeah. No, they should all sort of have different values. Yeah, we'll read the bands in a second. You'll see like how it will work. Yes. Oh, this one? Okay, so this image file, this second cell here is the path to the file, and that we've gotten through this line that we ran at the beginning. So here in this third line, the variable image file is this path. So when we do rasterio.open, we're opening the path that ties to that file. Oh, okay. I'm actually to be completely honest, this is the first time I've used Collab in this way with like the data actually in it. I'm not sure exactly how it's working, but it's this content part of the URL that is pointing it to this part. Yeah, if you download the data this way, as we've done here at the top, and then in Colab, you can use like /content and then use it that way. More questions? Oh, yes. Yeah, that's a good question. I think TIFFs do store more. Kevin, do you know? Oh, yeah. Yeah, I think it's because it's a geospatial image. It's like different from a regular, like a. I'm not totally sure on the mechanics of it. Yeah, I've had so many situations where I open up an image and I think like my computer's broken or something because it's all black. And then I realize that it's because it has extra bands or it's higher bit depth or something. So I have to open it on some geospatial software. All right, so now that we know how to work with rasterio, we're going to use it to extract bands and then compose a scene from it. So go ahead back to the repo and then open the second notebook, so 2_rasterbands.ipynb. And then same thing there, click on the Open and Collab button once you get there. And then you want to, again, run this. If you're using Collab, run what's underneath option 1. So get the data and then pip install rasterio. Are we all here? Yeah, great. Okay, so we want to first import our packages. So we're going to import rasterio again, like we just did, but we're also going to import numpy and also matplotlib. And I've just used shortcuts here. So here I'm just saying that every time I refer to numpy, I'm calling it np. And same thing with matplotlib.pyplot, I'm just calling it plt. By the way, I say numpy. I think Kevin says numpy. I don't know the right way to say it. All right, and again, we want to get our image file and then open it using rasterio. Ooh. Oh, yes. Okay. So first, we're going to look at the metadata of our image. So this first line, we're getting our image's coordinate reference system. So we see that this corresponds to UTM, Universal Transverse Mercator coordinate reference system. A coordinate reference system is basically when we're talking about Earth data, the Earth is round, so we're talking about it in a 3D way. And then when we are working with images, we're working with 2D images. So there's a bit of a transformation that has to happen from the 3D to the 2D, and that's what a coordinate reference system helps us with. So in this case, because we know that the coordinate reference system is UTM, UTM uses meters as the projected units. So we know that the units we're working with here, if we're talking about the projected coordinates, are meters. So here, this is telling us that the left corner, bottom, right, and top, these are the locations in meters. And what this is in reference to, it always helps me to look at this map. So just for general reference, UTM divides the Earth into 60 different regions, and each region is like 6 degrees wide. So this is what that's referring to within the region, the position in meters. Okay, we also want to get the dimensions of our image. So if we run this line, we see that our image is 25,000-ish meters by 11,000 meters width and height. And then we also want to get the rows and columns. So we see, this is in pixels, so our image is about 4,000-ish rows by 8,300 columns. And now that we have both the dimensions in meters and pixels, we can look at our spatial resolution. So if we divide the length in meters by pixels, we see that our image has a 3-meter resolution. So each pixel in our image is representing a 3 x 3 meter block. And just for a sanity check, yes, our pixels are square. I've never encountered a situation when pixels are not square, but just to sort of make sure that's the case. Yes. Yes. Yeah. 3 meters by 3 meters. All right. We also want to look at our pixel coordinates on the globe into geographic coordinates. So this is telling us that in the UTM coordinate system, that picture I just showed y'all, this is our top left corner coordinate and our bottom right corner coordinate. Again, sort of just like a sanity check type of thing. These numbers? No. That's a good question. These are, you can look at the eastings and northings. So I would have to look at this, find the zone that my image is in. Yeah, so this is referring to within the zone itself. So I would have to find the UTM zone and then go to that zone and check it from there. Yeah. Yes. Yeah, that's a good point. Thanks. Cool. And then all this, we sort of did this manually, but all this information is available in the image's profile. So if you run this next line, sci.profile, we see the bit depth, we see the pixel dimensions, band count, all this stuff is right here. So we can see that very easily. Questions about metadata stuff? Yes. Yep. Yeah, that's to do with this easting and northing thing. So within these cells, moving to the right goes up, and moving up, it gets higher. Yes. Ooh, that's a good question. Yeah, I'm not sure. Does anyone know? I would have to look that up, but yeah. Yes. Yeah, there is an attribute, I think it's called like the image dot transform or something, that will help you transform an image, or at least like get the reference system, then you can transform it from there. Other questions? Awesome. So now that we know a little bit about our image, we can use it to compose a scene. So again, if we look at our band count and indices, we have 3 bands, 1, 2, 3. And then again, we know it's a PlanetScope 3-band image, so we can assign our bands blue, green, red. So we have our bands here. And then here's the fun part. This is sort of what we were talking about earlier, where what Kevin was mentioning with the different bands and how they can be stacked on top of each other to get that visual image that we're used to seeing. So this line, numpy.dstack, we stack the red, green, and blue bands on top of each other. And so this, what we get is our visual image, something we can see with our eyes. And then to actually look at that image, we can use pyplot to plot it here. And here we go. Voila. Yes. Yeah, so it does look a little bluish. I've tried it in a few different ways. Otherwise, it looks reddish. It might just be the way that it's visualizing it here. I'm sure if we pulled it up and like calibrated the visual components of it, it would probably look a little better. There's generally some calibration that you need to do with images. In preview? Okay. Kevin, are you familiar with this? It might look a bit reddish if you do that. Yeah, I'll try. Yeah, this does look better. That is a good call. I know the order is BGR, so I'm a little confused. Yeah, that was a good call. Thank you. Okay. Got it. I changed it on line 17. Or, sorry. Yeah, line 17. So this is where it was RGB and we changed it. Good call on the I'm show. Thank you. Okay, so just looking at this image really quickly, it's kind of blurry, but we have flood water here. That's this kind of brownish stuff we're seeing, which it makes sense that it's brown now, because before it was oddly blue. And so this is good to know that we know we're looking for water in this top right corner of our image. So that's just something to keep in mind as we go. Also here in the left side, we have clouds that we're seeing. And also you see the clouds shadows if you look closely. This is also important to know because sometimes when we work with imagery, we're using things like reflectance values to get information about the imagery. And then sometimes because of that, clouds can read as water values. So if we're not careful, if we're doing like a classification or something, it might think that these sections are water, even though they're clouds. So that's why you kind of always want to look at your imagery, make sure you know what if you're looking at clouds or what you generally might expect. And we'll see this kind of play out a little bit later. Yes, yeah. So we've worked with rasterio to read in our data. And then we've also looked at our metadata associated with our image. And then we've visualized our image so far. Yes. Okay. So now that we have taken a look at our image, we can get into more computational stuff. So we can compute our NDWI, learn about it, compute it, and then calculate a landmass from that. Okay, so back to the repo, notebook 3, and then same thing. I'm sure y'all know the drill by now. Open in Colab, and then run this first line. All right. So again, we want to import our packages and load our data. Same thing as we've done before. And now we're gonna calculate NDWI. So in this example, because we're looking at flooding, it would be useful to be able to say, oh, this is an area of water versus this is an area of land, and get an idea of what we're working with without sort of not in a visual way, but more in like a computational way. So we can measure something called the normalized difference water index, or NDWI. This is related to plant water content, and it can help us identify areas of water. And we can calculate it by using our bands. So the calculation is green minus NIR, near infrared, over green plus NIR. If you're curious about NDWI, you can find more information here. You might have heard of also like NDVI, vegetation index. There's many different indices, and NDWI is just one of them. So the first thing we're gonna do when we're working with NDWI is we're gonna allow division by 0. This is kind of crazy. Like, I feel like middle school, high school teachers would like yell at you if you tried to do something like this. But the reason we're allowing division by 0 is because in our this is supposed to say NDWI. In our NDWI calculation, parts of our image might be clipped or might have like 0 or null values. And if this happens in the denominator of our calculation, we have this addition, and if both of them are either null values or 0, then we would have a division by 0. So by allowing division by 0 here, we're just making sure that if we run into any null or 0 values, that it doesn't break our code. Yeah, so that's just if this denominator is 0. We just want to allow that. It would just, I think it would just remain 0 or null. It's just allowing it so the code doesn't break. Yeah. Okay, so again, we want to read in our bands. And you might notice here, we have an extra band we're working with. We're working with the NIR band. This is because the past 2 notebooks we worked with, we were working with visual data, which is just like, you can see it with your eyes. You don't need the NIR band. This time we're working with the analytic file, and the analytic file does include that NIR band. So that's why when we read this in, we have this extra band we're accounting for. And then here we're calculating NDWI. So again, here's the calculation, green NIR, and we're dividing it. And then once we have our NDWI calc, we can visualize it. So same way that we visualized the previous image with IM show. All right, so here's our visualization of our data set. And you can see that this is showing the values. So the higher values correspond with those areas we saw earlier that we knew to be water, just from looking at it. With NDWI, pixels that have a relatively highish value, generally greater than 0.3, are generally associated to be water values, while pixels that have lower values are more unlikely to be water. But in this case, because we're looking at flooding data, the line between land and water is a little murky, the water is a little murky, we're going to be using a slightly lower threshold. So we're going to be saying that anything higher than 0 for now is going to be considered water. This is, you can kind of play around with this a little bit. There's not like a hard and fast sort of thing. This is something that people generally experiment with just a bit. That is a good question. I'm sure you'd have to do some more image processing if you wanted to get into like the nitty gritty. There's probably some other sort of calculations and things you would have to do. Masking would help. We'll talk about that in a second. But I think generally it's better for more like clear areas of water. Would you say, Kevin? Yeah. So now that we know our NDWI values and we've sort of established that we're using 0 as a threshold in this case, we can create a mask which says that basically anywhere where the values are higher than our threshold, which is 0, we want to call those water, call those pixels as water pixels. And then anywhere where the values are lower than our threshold, we want to call that land pixels. So that is what we're doing in this line here. And we'll work with this a little more in a second. Does that make sense to everybody? Are we all good with NDWI? Awesome. Okay, so now that we have our NDWI values, we can talk a little more about interpreting this. So what does it mean? How can we sort of get more clarity on what's water and what's land? So notebook number 4, back to our repo, masks and filters, and then open in Colab. Yes. openCV. Yeah, you might need to import it if you don't already. Gotta love the import errors. Are we all generally here? Yeah, okay. So this first part is kind of just doing exactly what we just did. So feel free to just run all these lines. Here we're just calculating the NDWI again, just in this notebook. So we're doing the same thing, allowing division by 0, setting the bands, calculating NDWI, and then getting their masks. So once we have the masks, we can look at them. So just to recap, the masks showed us, once we had our NDWI values, what pixels based on our threshold are we classifying as water versus land. So we can look at our masks. So first let's look at our water mask. And then let's look at the land mask. Yeah, it's kind of a funny image. It's like you look at this and you're like, what am I looking at? It just like shapes and holes. In the visual image we looked at, we saw this whole area at the top right was supposed to have water in it. We see some water here. There's a lot of holes though where we would expect a bit more water. Versus the land, it does make sense here. If you see this like curly shape here, that's where we did expect the water to be in our previous image. So that sort of makes sense. But again, there's sort of a lot of uncertainty around this image of where the land versus water values actually are. Yes. Yes. That is the clipped portion of the image. That was like NaN or like, yeah, zeros. Yeah. Exactly. Yes, that's what we're going to do. So that's where filtering comes in. So if we wanted to clean up this mask and get a better idea of where the land and water areas are, we can use filtering. The morphological filters we're going to use right now come from CV2. And there's a couple different filters we're going to use. One is called closing filters and one is called opening filters. I'm a visual person, so I like to look at this, what it looks like. So let's pull this up. This is from the openCV documentation. So you can see that an opening filter is when you have areas outside of your main image that you want to close up. Personally, I think the opening and closing, the terminology should be flipped, because for me, this seems more like closing. But anyway, I don't make the rules. So this is an opening filter where we're clearing out these extra specks outside. And then a closing filter, which to me kind of sounds like opening because we're getting rid of these specks. But anyways, we're clearing them out of the main part of the image here. So the way we do this in action is we establish a kernel size. So for our closing, I've just said 35, and then for opening, I've said 15. You can change these, feel free to experiment. This is saying that for the closing, any patches of pixels that are within this window of 35 will be closed. And same with the opening kernel. Any pixels that are within 15 pixels will be opened. And then the rest it'll ignore, it'll keep them the same. Um, 35. Sorry? Yeah. It's like a grid. Yeah. Say that again? Yep. Yeah. Oh yeah. It's a 30, it's 35 by 35. Yeah. So what we're doing here is applying this one's. Okay, there we go. We're applying first the closing filter. So we're doing, pull this up again. We're getting rid of where we do expect there to be the data we're looking for. We're getting rid of the holes. And then we have that mask, the closed mask, using this 35 grid kernel size. And then we're taking applying the opening filter on that closed data set that we already have. So That's why here you see we're applying it on the mask closed data. And then finally, this object mask underscore closed underscore opened is after we've applied the closing filter and the opening filter. And then this is what I think someone was asking about earlier, where I think you were asking about it. How do we make sure that the areas that, like, why were those areas black that were black before? And this is just making sure that the areas that were clipped earlier still remain clipped. We don't want areas that were 0, we don't want them factoring into the opening or closing. So that's what we're doing here. So we have our final mask, and then we can visualize it. All right, so let's just for reference go back up to our original water mask. This is what we had before, sort of, can't really tell a whole lot. This is what we have now, and you can see this part on the right. We can see much more clearly the areas of flooding that we saw in the visual image. Of course, there's still a lot of this stuff out here. I'm sure we're probably catching some clouds in there in this that's counting the clouds as water. This is something that you can experiment with. People run like algorithms and stuff to find the perfect combination of closing and opening kernels and other sort of things you can do with it. But here's just sort of a general idea of how this works to get a better understanding of the filtering. I think so. That's a good question. I'm not aware of the like actual dynamics of the algorithm. Oh.
Let's say each of these blobs is like a 5 by 5 or less. So if you say your kernel size is 5 or larger, it'll run through each row, and then it'll say, oh, is this 5 by 5 or less? If it is, then it'll just make it black. And that's why like none of this J is affected, because it's probably larger than the 5 by 5. And similar goes here. It'll run through all these pixels, and then if this is like a 5 by 5 or less, it'll close that hole. Again, which is weird because actually, I guess closing. I don't know. And then like I don't know, but like this is weird. This is weird that's opening, but I get it.
Thanks, Kevin. Questions on masks and filtering? This is great. We've done so much. We have worked with rasterio. We've read in our image. We've looked at our metadata of our image. Then we've talked about NDWI, what it is, why we calculate it. We've calculated it. And then once we have our NDWI, we have applied filters and masks to it. By profile, are you talking? I'm not sure I understand. So are you talking about like the area of the image that has data versus the part that doesn't have any data? Mm-hmm. Okay. Okay. Yeah, I see. Yeah, so this is something that if we were doing this for a bunch of images or doing it like again and again, we would have already identified like what are the characteristics of this image and how can we change our algorithm or refine it in a way to get at the pixels we really want to. I think the best answer is that it just depends, because with the way the imagery works, we might not get, like this image that we're looking at, we might not get this exact slice of the image. We might get a little bit above or below or to the side or whatever. And obviously, like seasonal changes are a real thing. So things look different times of the year, different seasons, different years. Also, like the land changes over time. So I think, yeah, they might not. Yeah. So there's a degree of calibration that's you would want to like sort of have set as the profile. But there's also always things that you're going to want to change depending on the image that you're working with. That's a good question. More questions? Yes. Yeah, those are pixels that the data set is just, we're looking at a particular part of the data set, and those are just like either 0 values or like clipped. Okay. Any ideas? Yeah, we'll have to look into it. So I guess with the clipped, I was talking about null values, like values that just don't show on either of the images, not just in the border, but like even in the middle of the image, there might be pixels that are just not there, which wouldn't show up. Yeah, it maybe it wasn't captured in the satellite, or maybe it was and it's just like corrupted in some way. Yeah. Maybe. I would have to look into it, honestly. I would have to like go in, probably look at the pixel values at the parts that you're talking about. But yeah, that's a good question. Yeah, there are areas that were black that are now not there. Yeah, but there's also some other areas in the middle of this image. It looks like, yeah. Yes. Yeah, it sounds like a very good guess. Thank you. Yeah. Yeah. The individual bands can also have values that are NaN. More questions. These are great, you guys. Thank you. Yes. I'm sure there is. Yeah. It would be really useful just to like cut out the whole class. Yeah. I'm sure there is. Kevin, do you know of one?
Like there are like ways you can detect clouds using like machine learning, for instance, but there's also much easier ways. Stuff that I don't remember off the top of my head, but like similar sort of spectral calculations where you can sort of get an idea of like how likely it is that an individual pixel is related to a cloud versus land or water. But this is like a super dumbed down, easy way. Yeah, but like there are tons of even like just like machine learning algorithms that are like, ooh, this is a cloud, but that gets really complicated because you can get like wispy clouds, or you can get regions that are like foggy, or you can get regions that are like filled with smoke, for instance, and it gets a little bit more nuanced. Yeah, but that's a really great question.
Even like there was an algorithm that Kevin and I were working with earlier this year that was about like snow. We were working with icebergs, and that got really confusing because you have clouds and you also have snow and then you have icebergs, and it all looks like water also. So yeah, it gets a bit confusing. Sorry. Well, yeah, you're right. It is all water, different forms. We found we were working on like different indexes to look at that, and we found like several different papers, like sort of technical papers that people have written that use different algorithms that we've tried. Yeah. Questions? Other questions? Cool. We're in the home stretch. We're almost there. I know we've been here for a while, but we'll get you guys a break soon. Last piece of this is we're going to just quickly look at plotting a histogram. So how can we use our raster pixel values to plot a histogram? So same thing, back to our repo, notebook number 5, plotting a histogram, and then open in Colab and run your data download. All right, so this one, first few cells, y'all should be experts by now. Import packages, get our data, and then open it in rasterio, and get our bands again. Okay, so this next code cell, there's sort of a lot of stuff in this code cell, so I'll just go through it slowly. We're first going to define a new figure and then a subplot. PyPlot is a little weird with this kind of stuff. It just takes a little bit of getting used to. It's a little bit confusing. And then we want to add a title and then X and Y labels to our plot, just so that we know what we're looking at. Is everyone familiar with like histograms and how histograms generally work? So histograms show you, they're a good way of looking at the distribution of your data. So you can see the data values and then the frequency of those values in your data set. So it just helps you get an idea of what you're working with. So in this case, we're gonna look at one of our bands. We're gonna look at our blue band. And we're gonna plot specifically non-null blue band values just to see what that looks like. Blue in this case, because we're looking at the flooding in Houston. So just to see if that corresponds in any way. We also want to define the number of bins. So this is arbitrary. I just chose 50. You can choose 150 if you want to, or like 5. Depends on the granularity you want to get to. You can also change the color of your histogram. And then here is where you actually call the histogram, where you tell it that that's the kind of chart that we want. And then you can also save the chart that you create to your computer, which is what this line is. And then finally we show it. So if we run this line. Okay, so what are we looking at? X-axis, we have pixel values. And then the y-axis shows the number of pixels in the 100,000s. So we see that the pixels, the highest number are around what looks like to be 7,000-ish, maybe 7 or 6 or 8,000, around there. I was curious about this. I was like, what is this showing me in blue values? So, oh, dang. Okay, we're on a different computer, so I can't show you here, but I pulled this up in QGIS, and I was looking at the areas of water in that top right corner of the image that we were looking at earlier, and the pixel values there correspond to this 7,000-ish value. So my guess is maybe there's more flooding in this image than we originally thought, or like maybe that more that we can see, and those flooding areas are maybe what's accounting for this higher blue band. But there's no, this was just like a quick sort of, I was curious about it. I would have to probably do a little more looking into to tell exactly. But this plotting a histogram will come in handy for what you'll do after the break with Kevin. Questions, comments, concerns? Yes. Does it speak to the radiometric resolution? Oh, yes. Yeah. Yeah, I think it does tie to that, because that's the range of pixel values that we're looking at in the band. Yeah. Mm-hmm. What do you mean? Oh, yeah. Like if it's clipped or something, yeah. Yeah, you would see it in the histogram. You'd see the values, yeah. But in this case, we're looking at non-null values. So null values wouldn't show up. But if there were, I don't know, some like corrupted values or just values like really high, you would see that spike. Yeah. More questions? Okay. Well, congratulations, y'all. You made it this far. You're still here. No one's crying or like left yet, so that's a good sign. So we just, a quick recap, we've gone through, talked about how to work with geospatial data, the components that make geospatial data maybe different to work with than other types of imagery. Then we've also walked through in Python, looking at rasterio, working with the bands, computing NDWI, masking and filtering, and then finally how to plot a histogram. So we will take a short break. I wrote this slide before I kind of knew about the timings. Maybe we should change this. What should we say? What time? 9:50? Okay, yeah. Let's take a short break. Let's come back by 9:50, and then after the break, we will have Kevin lead you through a specific example for coastline erosion. Sound good? Thank you.
All right, everyone. We're going to get started on this next section. So just grab your seats whenever you can. Can you guys still hear me if I go hands-free and use this mic stand? Yeah? Cool. Let's see if I can get that. Yeah, that's good. All right, so I'm Kevin, software engineer at Planet. My background is in astronomy and computer vision-y things. And I recently moved to Planet because I thought Planet was really cool and doing really cool things for the Earth. A lot of humanitarian resources being provided, and just doing a lot of really cool science. So I thought I would apply my scientific background and my coding skills to the test at Planet, and it's going really well. Not trying to sell you some Planet, but I love it. So for this next part, we thought we would take everything that we learned before and apply it to a real world example. That's not the thing. Whatever. So I thought, what would be a really good example? And I went through searching through papers. We have a whole list of publications on our website that use our data. And one of them was a region in Bangladesh that had a pretty severe example of coastal erosion. Coastal erosion is just basically a part of the coast that erodes inland. And we're going to be talking a lot about that. So what we're going to be doing is we're going to be importing and processing all the data as we did earlier in the notebooks, and creating a time series of that area of interest. I'll be referring to the area of interest as the AOI, just something that we do a lot in geospatial data. And then we're going to be creating the image processing pipeline that we did all in the notebooks, just basically in one big pipeline. And then we're going to classify regions of water and land, just like we did with the NDWIs or NDWIs. And then we're going to be employing just some classical computer vision techniques, nothing machine learning based, just more classical computer vision techniques to try and find how the coastal erosion is happening over that time series. And then we're going to pull out some cool metrics like the landmass loss over time and identify how much the coast has moved inward and is it slowing down or speeding up. For reference, in the very, very bottom in like tiny, tiny font, you can see that there's a paper that I reference. If anyone cares, it's also in the notebook, but it's this paper here. They're the ones who I stole the idea off of. they have this really great region of interest that finds just like coastal erosion just tearing apart that part of Bangladesh. And they have their whole analysis baked into here and also pretty pictures. So we're gonna get right into it. Let's go to the GitHub page. We're gonna be going to the one called Coastal Analysis.SciPy notebook. And then from there, we'll click the Open a Collab button. That should bring you here. So first thing we do, let's download the data. It's a lot of data. Run this wget command. I've done this while you guys are out, but this shouldn't take too long. You might get an error on your terminal or on your websites or on your notebook saying that you have too many active notebooks sessions. Thank you. I just did this. Is anyone running into that error right now? Yes, just terminate all the other ones. I really should have just waited to do that, but okay. Right, okay, so you see where it says RAM and disk up here? If you go to the Manage Sessions button, I've already terminated my sessions, but you can go here to terminate your sessions. In fact, I'll terminate these ones. I'll terminate the rasterio, first look, and raster bands. Cool. Once everyone has the data with the wget command, let me know when you're, I'll give you all like a minute. There's also a lot of text in this notebook. I mostly was just like writing down some thoughts as I was going through it. It's mostly just for like, just getting a sense of what's happening. I'm probably going to be reading from it, just as a heads up. Does everyone have the data downloaded? Yeah. Does anyone not have the data downloaded? Okay. All right. I'll give you like a few more minutes. In the meantime, we'll pip install rasterio. And then we'll import all the packages once that's done. Successful. Good. Then we're gonna use a few more packages here. We're gonna be particularly just using a SciPy package called Find Peaks. Well, we'll see what that does in a minute. That's for like the last little bit. Okay, so now that we have all our data downloaded and all of our packages downloaded, I'll just get a little bit into like what we're going to be looking at. So we're going to be looking at a specific region of Bangladesh, specifically the southern region of Bangladesh, where the ocean meets the mainland, and we're going to be looking at this inlet here, where there's lots of coastal erosion happening to lots of regions, but I'm going to specifically zoom into one region right here, and this little polygon I've drawn is like our area of interest. So when we're imaging it, you'll see that everything outside of this polygon is going to be black or white. Those are just like the cliff regions. That's what we call cliff regions. And then this is like the coastal region that we're going to be looking at. I've chosen the data to have like no clouds or very, very minimal clouds. So hopefully we don't see any of this stuff pop in just for NDWI reasons. Any questions so far? No? All right, cool. So just like before, we're going to be importing visual and analytic data. The visual data is going to be really helpful to just visualize what's happening. This image here is a visual band image. And the analytic data is like the full bit depth image that's like full color resolution at 16 bits. And then we're going to sort the data by chronologically. So we're going to start at the year 2017 and image it once a year until this year in 2022. In case you're interested, I chose the spring seasons where it's a little bit drier and there's less flooding. We can get more into that later if you're interested. So we should have 5 data points: 2017, 2018, 2019, 2020, 2021, 6 data points. I can't. Okay, and now we're going to be starting our image processing pipeline. Basically, what we're going to do is we're going to do everything that we did before in the previous notebooks and just code them in the function. So just going to put a function call around them. Is anyone here not familiar with functions in Python? Okay, so for those who aren't, pretty much what we're going to do is put the code that we had in our notebooks, and then just put a little defining function call around it. So def, we're defining a function. This here is the function name. In this case, it'll be called extract spectral bands. And then this is the input image file name. And then in this case, it'll return spectral bands. So here we're going to call an image file name. I do this a little bit differently than Mansi. I mean, to be honest, Mansi's way is much better, but I do this a little bit more archaic. I just open each band individually with rasterio. So I'm opening the green band and the near red band, and then I'm returning that to the user this line here. So let's just take a look at how this works. Actually, let me run this cell. So by running the cell, we let the notebook know that the function exists and how it works. And okay. So let's take a look at the second year in our data set. I chose the second year because it's a more dramatic example of what we're going to look at in a second. So second year, Python uses lists at 0, so we're going to start indexing at 1. And then we're going to extract those spectral bands. So to call the function, we just say what we're returning on the left-hand side, the function name, and then the file name. So we're going to be calling the analytic file the second data point in that analytic file. So we ran that. Now let's see what's happening. So here I've used pyplot.imshow to look at the green band. Yeah, I mean, nothing special, right? This is just the green band. And similarly, we'll be looking at the near infrared band. These are just pixel values on the X and Y axes. Not very helpful, so I'm just going to turn them off for the rest of the demonstrations. There are ways to turn those into like coordinate system values, but it's not worth it for this presentation, so I'm not going to do it. And here's the near infrared band. So you can see that like the near infrared is like super prevalent on land and like pretty not relevant or not bright on the water. And there's a whole bunch of science behind that. Basically, near infrared images heat, and water is a lot colder than air. Do you have a question? Great, cool. Green, a little bit more complicated. I don't really know the reason. Right? Things are different. Cool. All good on this section here. And we're using green and red to calculate the NDWI later. That's just why I imported them now. Next, I'm going to create a function to compose the scene, just like Mansi did earlier. So again, calling a function or creating a function with the inputs as the file name. And then again, I'm doing this a little more archaically than Mansi. I really should have updated this, to be honest. And I'm just importing the red, green, and blue band. And creating the visual image stacked with ND stack function call. And then let's call that function, create a visual image and a numpy array, and then let's do imshow to look at it. There we go. That sort of looks like the screenshot I took earlier. This is the 2018 image. You see land on the right, water on the left, and the clipped areas, which are just the areas that are not within that polygon, are just black. Those are actually NaN values in Python. And the water doesn't look very blue because it's very, very murky, sandy water. There might even be sandbars in there, or vegetation growth. Yeah. Any questions so far? Okay. Flying through this. All right, so let's compute the NDWI. As defined previously, the NDWI is just the green minus the near infrared over the sum of both those bands. Similar to how we did earlier, we're going to set the error of dividing by 0 to. So we're going to allow the division of 0. I'm pretty sure it sets it to a NaN value, but it might set it to 0. I'm not really sure. As I said, I'm pretty sure. I just realized I'm not sure. And then here we go. I just wrap the code in the function call, and then we return NDWI. Let's see what this looks like for this image. So I'm going to compute NDWI here, and I'm going to run imshow on that. There we go. Now this is a pretty dramatic example, especially compared to that Houston example. That water is like vibrant green, really, really high values of NDWI, and the right, the land is like so clearly not water. So the reason why is probably because in the Houston example, you have water on land, which can be a bit tricky. It's a little bit more difficult to unconvolve those pixels from like land values to water values, and it might be also really shallow water, whereas here we're looking at like the ocean. You can even see though, we have like rivers that go inland here, and these are like much less obvious values of NDWIs. There's even like little lakes probably, or ponds, probably lakes actually. And these are less obvious as well, but when the water's much deeper, it's much more clearly a value, much more clearly water pixel. That's a great question. Now, as Mansi mentioned earlier, we can classify pixels as water or land by just their NDWI value. We typically do that by setting a value of, thresholding by a value of 0.3. That's the typical value for our bands. But you can see here, nothing really gets up to 0.3. Like, maybe some pixels around here get up to 0.3. Otherwise, they're like more like around 0. Probably because this is like really murky water, really sandy water. Might even have like sandbars over here. It's unclear. We'd have to probably pass a higher resolution satellite, like our SkySat satellites, to get a better idea of what's happening. But for now, what we'll do is we'll set a threshold value, probably lower, maybe closer to 0, to just capture what's water and what's land. We'll do that in just a minute. Any questions so far? Cool. It's all pretty familiar probably from what we just did earlier, so I'm kind of like flying through it. But please tell me to slow down. All right, so here I just define a function that says find water and land. Oh, very creative name, but it gets the point across. So we're gonna take as an input the NDWI numpy array, and then we're going to return a water mask and a land mask. So we're setting our water threshold to be 0. We're saying anything that's above 0 in the NDWI array is going to be classified as water. Anything less than 0 is going to be classified as land. So we just do the thresholding just like we did earlier, and we return both water and land masks. So I'm going to run this code block. And then here, I'm running that code and I'm printing out just going to look at what the landmass looks like. So you can see how there's NaN values and 1s, there's also 0s, but it doesn't print out because it's actually a really, really large array. The NaN values are associated with those clipped areas. So if I scroll up a bit, you can see like the top left region is like all white. Those are all just clipped values, so just set them to NaN. And then down here, where it's bluer, those are going to be 1 because they're land. And that sort of aligns with what we see in the print here. But we'll take a look at the masks now. So let's visualize these masks. How good are they? Okay, here are the masks. You have the water mask above and the land mask down below. Did a pretty good job on the land mask. Water mask, like kind of not so much. You can see that like even though it's super obviously water, there are some holes in that water mask, and same with the land. So any suggestions how to fix those holes? Yes, filtering, morphological filtering, great. So we'll do some opening and closing filters to open and close those holes. All right. So I'm going to define a function called filter mask. So it's going to take in the closing and opening kernel sizes, which is just the width of the kernel box, and then the mask in question, whether it's water or land mask. And it's going to return the mask that has been filtered. So it's going to be a closing function followed by an opening function. So just identically as before, we're going to define a closing kernel element. We're going to initiate that closing kernel, and then we're going to apply that kernel to the mask. And then we're going to take the closed mask and apply an opening function to it as well. And it's going to return a mask that has been closed and then opened. That's a lot of words. Let's see what that looks like for real. So here I've like empirically defined some kernel sizes for opening and closing filters, specifically for the water mask and for the land mask. Now you can see earlier in the water and land masks, the water mask has like massive holes in it, and the land mask has smaller holes. And this kind of, I don't remember your name, but in the watermelon chart, you asked earlier about do you need to change the kernel sizes? Yes, absolutely. So even just for these two different masks, the kernel sizes need to be completely different. And in fact, like over the years from 2017 to 2022, you can absolutely have different kernel sizes. I just chose the maximum value for all of the years. And this will convolve best for like worst case scenario like this, and like the best case scenario has just small holes. And if you have small holes, big kernel sizes will still work. So I've defined these kernel sizes. So I'm going to use the filter mask function that we just created to create the filtered water mask and the filtered land mask. So it'll take a second because the morphological filters are kind of like long. Took 2 seconds. Cool. Now let's take a look at what the filtered versions of these masks look like. So now you can see that all of the holes have been filled. Great. Pardon me. And close in the river, that's right. Yeah, I specifically chose a value of NDWI that wasn't too low, not to capture the river that goes inland here. So in 22, you didn't see the river, but there are other years where you do actually catch the river going inland. And that's exactly right. You would probably see holes going inland here, and that would just smush them. That's fine, because what we care about is coastal erosion, which I haven't talked about much yet, but we'll talk about that in a second. Right now, we're just capturing the land and water mass filters. Any more questions? Yeah. There we go. So now we have 2 very distinct masks, water mask and land mask. So this was just for 1 year. So now let's run like this entire process for each of the years. So from 2022 to 2017. So here's like this little pipeline that I've created. There's a lot going on, but basically we're going to run everything we just created. So we're going to loop through each year. The first thing we're going to do is extract the spectral bands, the green and red band. Next, we'll extract the visual image. This won't be used, but what you can do is you can just like visualize this image by putting like an info call around that visual image, just for fun, really. We'll compute the NDWI. We will take that NDWI and create water and land masks. Afterwards, we're going to take those masks and filter all those little holes in them to create really distinct water and land masks. We're going to call them water and land filter, or water mask and land mask filter. And lastly, what we're going to do is something that we haven't done yet, is we're going to take all the land masks and add them to an empty array. So up above, I created an empty array. Those who are really nerdy and care, this is like probably not the best way of doing this because you're just like expanding the array every time, so it's like a little bit slower, and the computer doesn't like it very much, but for this purpose, it's okay. So we're going to add the large landmass to the array every single time, and we're going to use that for analysis later. So this takes a second to run. So let's run that. In the meantime, are there any questions as like what's happening here? Or like why we're doing this? Yeah, ties are really tricky and it's really tough. So so I didn't grab the same data that the authors took. I kind of went rogue and did it myself. but there's a lot of consideration when grabbing these images. So I grabbed them in the dry season when it's not like super wet and you can have lots of variation in water. I grabbed them when there weren't any recent hurricanes or anything like that. I also grabbed them all within like a month of each other. And then the next thing I did was I also made sure that like the time of capture was like within within like half a day of each other. Exactly for that reason, to not capture high tide, low tide. That's a really important thing that I didn't think about until like the very end. Yeah. 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 So I almost certainly am including some tidal differences in these images, but from what we'll see in a minute, it won't really matter in the end. The coastal erosion is so much more dramatic than the tidal differences. But if you're looking at a much lower cadence, say like quarterly or monthly, the tidal differences would make it huge. Yeah, yeah, or just a flat. Yeah. So there's some reason of error from tidal differences. I'm not sure what it is in Bangladesh, like how far up the tide goes, but in some parts in Canada where I live, the Bay of Fundy can have the tide go out like kilometers. Don't quote me on that, but like a very you can't see the water. You can Google it. Really. All good. Okay. Has everyone run that for loop? Is everyone all good? Cool. So, cool. So now we're going to be analyzing coastal erosion. So what we're going to do is we're going to take a look at those land masks over each year and see how they change. So the first thing we're going to do is look at what I call land difference. So I'm going to take the first year, which is 2017, and compare that to all of the other land masks. So specifically, I'm going to subtract the land mask from 2017 compared to 2017, 2018, all the way to 2022. So you might imagine the comparing 2017 to 2017 will just give you a bunch of zeros, and 2017 to 2022 will just give you like the total mass loss. So this first cell, I'm just going to do that land difference. I put an NP nan to num call around that just because subtracting nans is like a pain in the belt, but this makes it really easy. And as Mansi mentioned earlier in the slides, the resolution of our pixels is about 3.7 meters. In Mansi's data set, it was 3 meters, but in this one, I checked the metadata and it's 3.7 meters. I really actually probably should have just called it from the metadata, but I didn't. And then the area per pixel is just the resolution squared, so length times width, because it's a square pixel. And then now we can take a look at the total landmass loss. So what we're going to do is we're going to look at that difference in land from, so land difference is actually not what I said earlier. The land difference is 2017 minus 2022. So we just see the total land lost in those 5 years. And so I'm taking that array, it's going to be in pixel values. So I'm going to multiply that by a physical unit, area per pixel, and then we're going to be able to get that in terms of meters, or square meters in this case. And in fact, it was so large, I multiplied it by 1 millionth. So we see that the total landmass loss is 11 million square meters in 5 years, which is pretty dramatic. But let's see what that looks like, because numbers can be funny sometimes. There we go. So this is the difference between 2017 and 2022 land masks. And you can see in yellow is the total landmass loss. You can get into nuances here, but up here they put a little seawall or like something in the way, so the land didn't really recede too much there. But over here in this coastal region where it's nice and soft, that receded a ton. And in like the small 7-kilometer strip, they lost 11 million square kilometers. So massive. Any questions on what we're doing so far? Okay. Now we're going to take that landmass loss and look at it over a time series. This might be a little more interesting. So I'm going to define a time array. Oops. Basically just saying like, how many years are we looking at in a numpy array. And then the next thing we're going to do is look at the, what I mentioned earlier, which is landmass loss over time. So not just comparing 2017 to 2022, but just comparing to every single year that we stored in that list. Okay, that's run. And now we can look at it in a time series. So we'll have we have years since 2017 on the x-axis, and on the vertical axis we have the total area loss in 100 or in 1,000 square meters. So you can see not only are we losing land mass, but like we're losing it quickly, and it appears to be speeding up. Pretty dramatic. These are things that like governments would want to know. Like, are we losing land? Number one, yeah, we are. Is it increasing? And not only is it increasing, but it looks like it might even be accelerating, which is bad news. So let's take a look. How quickly is it increasing? So we can measure, in this case, like the velocity of landmass loss. So just simply like the change in landmass over the change in time will give us like an idea of how quickly we're losing landmass. So we can do that with np.diff. Really helpful. It just takes like the last number and just subtracts from the previous number. And we're going to do that with the landmass loss and also the difference in time. And for those who cared, we're just basically taking the derivative of this function here. Let's take a look at what that looks like. So here's the speed or velocity. Well, there's no direction really. So the speed of the landmass loss per year. So you can see not only, like we were saying earlier, are we losing landmass, but we're like really quickly losing landmass and it's speeding up. Yeah, really fast too. I think I measure, at the last year, so this year, they're losing land at 225,000 meters squared per year in that small strip. Any questions as to like what's going on here? Yes. Yeah, just like not enough resources to keep up with like the changing, with like all the sea levels changing. So climate change is a big issue, and the land is being eroded due to the water levels changing and the more dramatic weather system effects. And the land there is really, really soft, so it just gets eroded really quickly. Bangladesh is not the only place that is land like this either. Lots of places around the world are, including the US and the UK. Lots of places that are like really heavily populated and have lots of resources too. So yeah, it's pretty dramatic. Yeah, it's a pretty real fact. And there's a link to the paper up above, and like they go in detail, much more than I could like read back to you. Okay. But yeah, it's pretty dramatic. Yes. Yes, totally. So a big part of this was just like me going through the data and then going through first, does anything look off? And then like this is like a week of work actually. So there's a lot of the behind the scenes work is like seeing if the data looks anomalous. So yeah, was there a flooding event? Was there a hurricane? Was there any of this sort of stuff? I pretty much just used Google, and I just looked when in southern Bangladesh were there region or times of flooding or any of these sort of special weather events, and I just pruned that from the data. So I just didn't choose those times. Mostly this time of year in the spring, it's pretty dry. They have monsoon seasons in the fall and winter, so choosing data in that time would be much riskier. If we were to do this at a higher cadence of like say monthly or quarterly, I'll go back to this plot here. Landmass loss probably wouldn't look like this. It probably would be like, it would look like it was going up, then maybe going back down for the different flooding events. This is more just like a smoothed out version. That's a really good point. Yeah. That being said, I haven't done that. I haven't gone through it at that low of a cadence or high of a cadence, so I don't know, but I imagine that's what it would look like. Exactly. Exactly. And like from tidal effects as well, you also see it moving around. So yeah, it gets pretty tricky. And these satellites don't go over the Earth at the same time every day. So you'll capture it different times of the day as well. Yeah. Yeah. That's a really complicated like analysis. But yeah, that would be a really good way of doing it. We haven't done that here, so but yeah, that would be a really good way of doing it. Okay, and then one of the next things we're going to do is just look at like, sure, it's we're losing land and we're losing it quickly and it's speeding up, but is it accelerating? Like, is the problem getting worse? And we can just do that by taking the derivative of the velocity, or we're taking difference of the velocity over the difference of the time, and we'll run those cells. And what we can see is that not only is it speeding up, but it's accelerating quickly. Now it looks like the acceleration is like slowing down, so that's a good sign, but it's still accelerating, which is not great. So if the government were to do all this analysis and take a look at the data, they'd probably get pretty concerned and say, "Hey, we should probably intervene." But yeah, it's pretty crazy. So that's sort of our spatial work here. Now we're going to go on to looking at specifically like how much has the land receded inward. So we looked at how much land was lost. Now we can look at like how much has the coast eroded. Any more questions? Cool. So we're going to be using a so there's lots of ways of doing this. You can just do it by hand. It's probably like the easiest way of doing this. But if you wanted to automate this, let's say you have like a pipeline and you want to like, you don't want to touch it. You just kind of want like let this thing run in the background with like, I don't know, 50 or 100 or 1,000 different regions in the Earth. This is like maybe a good way of doing this. So we're going to be using, we're going to be looking at that image. Hold on, I'll pull it up. This one here, the cumulative landmass loss. And this image here tells us a lot. But specifically what we're going to be looking at is, we're going to be looking at the left side there and the right side. The left side is the coast in 2017. The right-hand side is the coast in 2022. So all we need to do is find both those coastlines and then look at their position in the x-axis and see how much that position has changed. So here we go. So what we're going to do is we're going to take that image, that mask, and we're going to run an edge detection algorithm on it. There's lots of ways of doing this. You can run it by hand, or you can use openCV, which does it all for you. Highly recommend the second method. There's also different types of edge detection algorithms. I'm going to be using the canny edge detection, just as the one I'm most familiar with, but you can also try different methods. Yeah, let's run it. So it takes in the land difference image, which I just pulled up. I'm saying there's a threshold of 0 and 1. 0 is all the areas that like, well, 1 is the landmass lost and 0 is not. And then we're going to run the cell. But really the important part is going to be visualizing it because I don't think I can do it justice. There we go. So on the left-hand side is that coastal region on the 2017. On the right-hand side is 2022. That's great. We found the coastlines. We also found a bunch of other stuff in the meantime. We found like that part at the top, found the parts at the bottom, and like we still haven't been able to like automate where are the coasts. Now I'm gonna do some magic stuff. This really only works if your coasts are vertically oriented. This won't work if like you're looking at the image sideways or like on like an angle. This barely works for this image, but it works. So we're going to be creating a histogram. So the next thing we're going to do is we're going to take these coastlines or this edge detection algorithm output and then bin up all of the coastal pixels from left to right. I'll kind of go up and just make it explain a little bit better. So we're going to be looking at like how many pixels do we find that are yellow as we scan across from left to right. And one might expect that you might find lots, like 0 pixels here, a few pixels here, lots of pixels here, a few here, and lots of pixels here. Maybe. Let's find out. So what we're going to be doing here is we're going to look, we're going to be creating a histogram with numpy. I created just like a random, or not random, I chose 12 things for this. And then what we do next is we take that histogram. In fact, I'll show you the histogram first. And I want to find these peaks. The way I found these peaks, there's lots of ways of doing this. You can do this by hand pretty easily, but like, why do it by hand when someone else has already done it, right? So I use the SciPy package called find peaks to just find the maximum values in the histogram. Yeah, pretty straightforward. So these values here correlate to the coastal regions. And to show you that, I'm going to show you the edge detection output with an overlay of the, it's not really clear on this screen, but with an overlay of that histogram. And this region here is the 2017 coast, and this is the 2022 coast. Like I said earlier, it's not like the perfect way to do it, but like it's a pretty good way to do it. Yeah. Any questions on that? Yeah. Oh, okay. So the heading detection works. It works on this data in general, but this histogram method of finding the coastlines will only work when it's vertically lined because of us scanning left to right to see where the pieces are. If let's say the image was oriented in like a way that like the coast was eroding this way, we wouldn't be able to find it. Like we would just find pretty much just like the histogram would have like a peak here because the coast this would be oriented this way. So we'd probably find a pretty uniform distribution of all the pixels. Yeah, totally transpose it. Yeah, but I chose a pretty convenient data set, so we didn't have to do that. Transposing comes with its own issues. You interpolate data, which can get a bit funky. But yeah, you can transpose it, or you can also like when you download data, you can also get it pre-transposed. Yeah. Cool. And now we want to see how much the coast has eroded inland. So we just take the difference between the two peaks. So there we go. So the peaks are at right. The peaks are defined here in cell 33. And then I literally just take the difference of those two peaks and pull that recession, and then those are pixel values still. So we can multiply that by the resolution, we get the physical value, and then we can see that the land has receded about 2 kilometers in the past 5 years. And if you want a more general sense of like how much that's receding per year, on average, it's receding about 400 meters per year, which is like pretty dramatic. And that's kind of like the end of this. This was pretty quick because you've already learned all the things that I do with the functions. But do you have any more questions? Yeah. Yeah, it's pretty convincing. Yeah. Absolutely, yeah. Yeah, I mean, it gets a bit tricky, but like, you obviously want to catch it before you've lost 2 kilometers of coast. And like catching it before that can be a bit tricky. Let's say we take a look at this plot, right? Between, year 0 and year 1. So in that 2017 time, obviously like there's coastal erosion, but like you've only lost, well, it's still a lot. You lost about 400 kilometers of coast, which is 400 meters of coast, which is like a decent amount, but might not be very convincing. And if you add more data points in between, yeah, you might get a lot of variation from from tides and special weather events. So yeah, it can be pretty difficult to get convincing data. But when you add even just like 1 year here, right, like it's a pretty clear trend. Yeah. Totally. Yeah. Cool. So oh yeah. So yeah, that's a really complicated process. That's something that we don't deal with. That's we have a whole data pipeline team that's dedicated to that. Yeah, to do this. Yeah, like this is like an ongoing issue with like geospatial data in general. Um, it's called, I think, image rectification, and it's a really complicated processing. But it's a really complicated processing. Like, is this pixel in this image associated to the same permit in this pixel in the following year? So these are just like final analytic and visual products that like have already been rectified. Um, Getting the raw data, I mean I think even in like the like raw data that you can download, I think it's already rectified there too. Um, it's a yeah. Yeah, so these satellites are all like they all have on board like clocks, and when they go over different parts of the Earth, they communicate with different land stations. They have like pretty a pretty good sense of like where they are in space relative to Earth. Um, but capturing an image and sending it back to Earth with all that metadata is a really complicated process. Like taking all this metadata with like raw image and like converting that to a TIFF where you have just like all that data associated with it, and where you can say even like this pixel here, a 3 by 3 pixel, uh, we have a high certainty of like that has this coordinate. Like it's a really complicated process. And then there's even the whole process of like there's even a whole issue of when the satellite's not perpendicular to Earth. So you can have it like offset a bit. So if it's like let's say 88 degrees, right? The pixel is at the top of the image. exactly won't be as square as the pixels at the bottom of the image. So yeah, it's yeah. Yeah, yeah. So all of this stuff is done by like a whole team of people. It's a really complicated process. Nothing that I can speak to because I'm not doing it. I just get the pretty images. Yeah, so they have a wide background. Yeah, so a lot of them are programmers. Some of them come from like geospatial backgrounds. Some of them just come from like computer science backgrounds. Yeah, like myself, I've never worked in geospatial until I started to kind of just have like we just know Python and like how to apply it to different applications. Yeah. Yes. Yes. Right. So yeah. So good question. So that's called mosaicing. This is actually not one image. I think this is a combination of four images that have been mosaicked together, which is also also a whole other issue itself. Um, so uh, 'cause what happens is as the satellite goes over Earth, it does something called like what's called like a line scan. So it scans the Earth in the line as it rotates. So you don't get like one strip of the Earth. You get like like an elongated strip of the Earth. And as more satellites go over, it covers more area. And to get like a larger area like this, you need like in this case 4 different satellites to mosaic together. Yeah. Yeah, so solar reflection off of water is a whole different issue in itself. There's lots of issues. There's a lot of like problems to solve in geospatial imaging. Yeah. Even actually, you can even capture images of airplanes flying through the sky, and you can see them being captured in different spectral bands at different times. So as the image is taken, it's different on different satellites, but on our satellites, they're each band is taken uh, like after another. So like I don't remember the order, but let's just say red, blue, green, or like red, green, blue. You'll see like basically a rainbow of like of an airplane moving through the sky. And if you know for instance the speed at which you're orbiting, and how quickly you've captured images, you can get a sense of how fast that airplane is moving. Yeah, it's pretty cool. Yeah, well, yeah. Well, you can also use different software, like a flight tracking software, and you can associate images and be like, oh, this is like Air Canada flight 342 going to Tokyo. I don't know. Yes. Mm. So the high resolution ones are called SkySat. We bought those, pretty sure, from Google. Do you know how long we've been offering them for? Not sure. Yeah. Yeah. Ton. Like terabytes. Terabytes per day. Yeah. A lot. Yes. Yes. If you have like a Planet account. Yeah. We have data back from 2011. Yeah. Daily entry. Yeah. A lot of data. Yeah. Yes. Right. So we provide imagery. Then we also have like an analytics team um, that do certain type of analytics, like let's say road detection or like change detection. They can find much more much more sophisticated way than this, like the change in water levels, and you can find flood regions like in Houston. Yeah, like we'll get contracts from different companies or different groups, or sometimes like the Red Cross, for instance, to find to like do specific analysis.
Government, yeah, we just have we do business across several different industries. And also one thing about Kevin, you mentioned earlier something about an airplane. Just to be clear, like our imagery is high resolution, but it's not so high resolution that like you could look and like, oh, there's Kevin giving a talk at SciPy. Like you couldn't see individual people, so that is something that is important to keep in mind. I think Planet's philosophy is that we have to abide by all of the US's regulations and all that, but we take the imagery, and it's whoever wants to get the imagery from us can do that. Yes.
So like the US can't sell imagery to everyone, but whoever's abide by those laws can. Yeah, but like they're not like spy satellite resolution. Like you can detect roads and cars, but not like spy level. Yeah. Yes. Yes, it is. So the stuff that we were looking at was surface reflecting corrected. Yeah, you can choose to download it uncorrected and do it yourself.
There's also a whole, just like Kevin mentioned, the whole like rectification team that's in charge of that. There's a whole other team in charge of like making sure visually the images look good. That's like a whole other process. It's not as easy as like, oh, we downloaded an image, like there you go. There's like a whole sort of thing that goes into it. So
yeah, like you can take the analytic image and then do the same sort of numpy.dstack and stack the red, green, blue together, but it'll look awful. There's like Mansi said, there's a whole team that just goes through color correction and applies color science to make the image look pretty and visually appealing, and also like accurate. That's the hard part, because when you have shadows or you have clouds or you have like reflecting things on the ground, it can be really tricky to get a good image. Yeah, that's a good question, because I don't have an image of this on my laptop, but our spectral bands cover like different regions of the spectrum and different satellites. So we try to align ours with Landsat, I believe. So because they have like such a massive database, that it would make more sense to align with, just to have them all cohesive. But they're not perfectly aligned. So like the NDWI that we create will be a little bit different than the NDWI that you get from Landsat. And so the threshold that you get for a planet image would be different than it would be for a Landsat image. Yeah, like if you have the right threshold value, you can probably get a pretty similar mask. Yeah. Insurance company? Oh, I don't know.
sounds like a great idea.
If there's no more questions, those are our emails. We have our cards up at front if you want to message us there. We're also still in the Slack channel for how much longer that's open. And here's our team's website, so developers.planet.com. That's where you can find all things developer related. And then we have, I'm not kidding, like I refer to this all the time. It's called Planet School. It's basically a much more sophisticated version of our presentation, going from like bare bones, here's like how to use Python for geospatial things, to like much more complicated processes. And they have Jupyter notebooks that Mansi creates, and it lets you know how to like just be like a pro with Python and geospatial. Yeah, I don't know where, but we will have this. So we're creating a blog post for this SciPy event, and we'll link this YouTube. I'm pretty sure this will be on YouTube to the blog post. Cool. And if there's no more questions, we'll leave this up for a bit, and Mansi will just be hanging out, and we can take a look at the dove and talk to you. So, yeah, thank you.